So these are the notes for standard 3.3, the second component, which is solving problems using Newton's first law when there are angles. So just like projectiles, we can consider physics quantities that have angles in two different components so that we can consider how they would affect the motion of an object in the x direction and in the y direction. And so we're going to do that with forces as well um, by relying on what we know about trigonometry. Here's an example of an angled force shown in purple. And so we can split this into a y or vertical component and a x or horizontal one, and then use how each leg of the triangle is related to the angle that we know. And then we can multiply this full magnitude of the force times either the sine of the angle to find this component or times the cosine of the angle to find the adjacent leg. Also, for this slideshow, just remember that when an object is not accelerating, then it has balanced forces. And so when we say that the forces are balanced, we mean that separately in the x direction and in the y direction. And so they should be balanced in the x direction, and then the forces in the y direction should be balanced with forces in the y direction. And we'll see that in a problem today. So for our first example, we have someone who's testing a three-way tug-of-war game, and the designer sees that all three contestants are stuck, which means they're not moving. Viewed from above, the situation is shown down here in this force diagram. And so what we're trying to figure out is what is the strength of this force right here? How hard is that contestant pulling? So it would be useful to consider, since this component is just in the x direction, I'm going to color code it as blue. And since this force is just in the y direction, I'm going to color code it as red. But since this force is at an angle, really what we need to do is we need to think about the components of that force in the y direction and in the x direction. So for each person to be motionless, the forces in the y direction must be balanced, meaning that the y component of the purple force and this bottom force need to be equal. And then the same is true about this force pulling to the right that we don't know yet, and this force, which is the x component of the 40 newtons pulled up at an angle of 30 degrees. So that's all shown here with those congruency lines. In order to solve for the y component, we can multiply the total force of 40 times sine of the angle of 30 degrees, and we get that that's 20 newtons. And so that's good news because now it shows in our diagram that there are 20 newtons pulling upwards and 20 newtons pulling downwards. And so since those are equal, that means the y direction is balanced. But now we need to consider the x direction. So for the x direction, we can solve for the strength of this component, which is 34.6 newtons. And then we can say, well, the force pulling to the right has to be equal to this force so that they're balanced. And so we can say that the unknown force is 34.6 newtons to the right. For our second example, we have a child that's pulling a 4-kilogram toy at a constant velocity along the ground, and the child pulls using 10 newtons of force at a 50-degree angle. We need to find all the forces acting on the toy. So first, I'll draw a force diagram, and this is somewhat complicated to see with the picture. So here's our force diagram. We have a gravitational force pulling down, a normal force from the ground pushing back up, and then the child pulling this toy at an angle with friction between the ground and the toy. Notice again that I color-coded vertical forces as red, horizontal forces as blue, and then this force that's at an angle is purple, but we can split it up into two components that fit into one of those categories, so horizontal or vertical. We're going to consider the x direction first. And so if we look at the x component of the tension force, we know that that's going to be equal to the friction force because these are the only two forces acting in the x direction. So they need to be equal to one another in order to be balanced. So if we find the x component, we can do that by multiplying the hypotenuse times the cosine of the angle, and we get that the x component is 6.43 newtons. And so then the friction force has to be balanced. And so we can say that the friction force is the same strength, just going to the left. The y components, or the vertical forces, are going to be a little bit more complicated. We know that we can find the y component of the tension force by multiplying the full tension force times sine of the angle. And we know that we can find the gravitational force acting on the toy by using our equation. Sorry about those tools there. So the mass of the toy times 9.8. But we can see very quickly that 39.2 newtons and 7.6 newtons aren't equal. And that's okay because they don't have to be equal since there are three forces in the vertical direction. What that means is that the gravitational force is 39.2 newtons down, and so there needs to be a total of 39.2 newtons pulling or pushing up on the toy as well. And so that's where our calculation is going to come in. We're saying that there has to be no imbalance of forces. So all of the forces that are pulling or pushing up on the object need to be equal to all the forces that are pulling or pushing down. Then we can rearrange this equation and solve for just the normal force, since that's the one that we do not know yet. And so we see that the normal force has to be the rest of the force that the tension force y component isn't providing. And so we can find that there's 31.5 newtons that are unbalanced. And so those 31.5 newtons are going to be provided by the ground, where the 7.6 newtons are going to be provided by the tension force. So then our finished product will look something like this, with all of the strengths of the forces applied to the force diagram.